AP Stat students. So today's lesson, we are going to be running hypothesis tests. So you'll want to make sure that you have your calculator with you right now during this video to practice. You're also going to want to make sure you have your formula sheet either printed or pulled up to reference. I'll be showing that on screen, but this is something we got to practice right now, is running these significance tests. But you will need that formula sheet, and I'm going to be referring to it through this video. Okay, go ahead and get started. Alrighty, so we're going to do two examples. There are four in here that I want to do, but we're going to be working this first one here and then this one here. I have put up a worksheet for class on KITM. That's something you can start working through, as well as the problem set. That's what I would like you to start working on. As far as this class goes, we are going to be testing over this unit on the 14th. Okay, so that's next Wednesday. So this week we're really focused on practicing and making sure we understand how to run these tests and understand that pretty well. Okay, there's a lot to write here. If you feel like you want to write it, that's fine, or you can just reference this video later for the work. We are going to be taking notes over this problem to start, just to sort of get us into the setting for each one. So let's go ahead and get into it. So here we have a potato chip producer. They've received a truckload of potatoes from its main supplier. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Carry out a significance test at the alpha equals 0.05 significance level. What should the producer conclude? So when we are working these problems, there's a list of steps that we want to follow for this. Okay, first off, there's the types of tests that we want to know. So first off, you can write p-hat or x-bar, right? This is just like the last two chapters that we've done. We always have to interpret the question, is it p-hat or is it x-bar? If it's p-hat, we're going to run a one prop z-test is what it's going to be called. If it's x-bar, we know sigma, it's a z-test. If it's sigma is unknown, it's a t-test, okay? So all of that should be familiar, except we're changing out the word interval for test because it's hypothesis test. Make sure you write that first, and we're going to go back to our slider. If you need to rewind and write that, then do that. But is this x-bar or p-hat? That's what you have to be able to interpret. Which one is it? While reading the question, for it to be x-bar, we're looking for the word mean. We're looking for standard deviation. Those are the big keywords we're looking for. For p-hat, we're looking for percents, or the word proportion, or a fraction of some sort, or a part to whole. And right away, what stands out is this 8%. So that is an indicator that this is proportions. Okay. So we've got a list of steps that we want to follow when we're doing these. First off, we want to set up the hypotheses. Okay, we're going to run a significance test. We're going to have to set up the hypotheses here for this. So what are the hypotheses? Well, you always have the HO and HA, the null and alternative hypothesis. So what is null and alternative hypothesis? A review, because I know it's been a while. We've just got off spring break, but this is what we had talked about before then, setting up these hypotheses. It's only ever going to be mu or p. Well, it can be one of those, and it just has to make sense as to what you picked here. Is it mu or is it p-hat? Or excuse me, is it x-bar or is it p-hat? Well, we know it's p-hat, so both of these have to be in terms of p. These are always in terms of the parameter. Okay. That's going to be the first start of your setup. Every time it's going to be one of those symbols, you just have to pick the right one. Next, we always know that this is an equal symbol. Okay? Always. So I would say, as far as setting up your hypothesis, that is the beginning for all of them. They always start like this. And those are pretty easy things to determine. Now the next part would be you're going to have to read this question to figure out what values are going where, because this can only be a less than, greater than, or a not equal to symbol. So I would start there. I would look for, what are we trying to show? That's what the alternate hypothesis is. It's what we're seeking evidence for. Well, what is this producer trying to show? They're trying to find convincing evidence that more than 8% of the potatoes in the shipment have blemishes. So that right there that's telling us something. More than, right? More than 8%. So we put that as a decimal, not as a percent. More than 8% going to be or have blemishes. We're trying to find evidence for that. Now, automatically, as soon as you figure out what the number is, these are always the same. So that's what's nice. Once you get one of the values confirmed, this is always going to be the same. Okay? There we go. We got it. Now, our hypotheses. We have set those up successfully. Plenty of practice for that as we continue. You're going to have to set up your own hypotheses, and that might be where the first mistake happens because it is the first step. So make sure that you are careful when you're setting up. Next, number 2, you want to check the conditions. We've done this. This is the 3rd chapter. We've had to check a lot of these conditions. So what I'd like you to do is you can get by putting just the bold text. That's fine with me. I would like you to put this for the last one at least. Okay, what I've highlighted there. I think a lot of you know the 10% condition. You may want to put just this part here for that one, 10%. So random, 10% condition, large counts condition. That shows normality, independence, and unbiased. That's what we've talked about those countless amount of times. So we're going to check those. Is it random? Let's read the scenario here. Yeah, we see the word random here. Is 500 less than 10%? Well, we imagine it's a very large truckload. So, as long as there's at least 5,000, we're good, which it doesn't really say, but we've been through this. We know that normally we can just assume that it's significant or sufficiently large. So that's fine. And then lastly, we need to check the N times. This is P0. So that's from the null hypothesis. That's what we want there. Okay, for this one. So N is N is 500 times P sub 0, which is 0.08. Is that greater than or equal to 10? And then we want to show that 500 times the complement of that, which is 0.92, is greater than or equal to 10. So I'll just pull out my handy calculator here, which I've already done the calculation. I'll do it again. 500 times 0.08. So that's 40. So that means that this is good. Automatically, this is 92%. This is 8% of 500. This is 92% of 500. Yeah, that one's going to be good too. So we have checked all these conditions. Boom, boom, boom. Now we're ready to actually run this test, run the significance test. So we'll write this in your steps. Run the significance test. Says use the normal distribution or T distribution tables. But first we have to do, it's called calculate the test statistic. Okay, calculate the test statistic. And I'm going to even amend this. Then use the normal distribution tables or the T distribution table to find for P or the P value. Okay, so that's what we want to do. So how do we calculate this test statistic? Well, that's on your formula sheet. Let's go over to that formula sheet. So it's right here. Standardized test statistic. This is what we want. So we have statistic minus parameter, and then you have the standard error of the statistic. So that's what we want for this. So I'm going to actually copy and paste that. We'll see how this translates over to our test statistic. Let me adjust this back to the main display. Okay, so there's my there's that formula that we need. So standard error of a statistic, we have all of these over here in our formula sheet as well. We have this one, we have, we have these here, standard error of the sample statistic, right? But I want to make sure that we get the specific one that we need for proportions. So we want to make sure that for ours, this is a difference. We're using the null hypothesis for this instead of just p hat, because we don't really, like, we can find the sample proportion since we know we have 47 potatoes, but we want to make sure that we're using, to get our standard error for that, p0. Okay, so this is truly the specific one that we need here to find this test statistic. So let's go ahead and let's write that up in a slide. So to find our z, because this is a z test, we're on step 3 here. So we want z equal to, well, we need our, we want our statistic. Well, what is the statistic? Well, that'd be 47 divided by 500. So 47 divided by 500, 0.094. So we're going to write that in 0.094 minus, well, we want to use our parameter. Okay, so that's p0 is 0.8. That's what goes up top for this using that formula. The last thing we need is the standard error. Okay, so we just saw that formula on the bottom. So we use square root. We want p0 times its complement, which is 0.92, over n, which is 500. Right here should give us the value that we need. So let's talk about what is the most efficient way to type this in. Well, you'll definitely want to start by hitting Control Divide to get a fraction. We're going to go ahead and type in exactly as it shows, minus 0.08. Okay. We're going to make a radical, Control x squared, make another fraction inside of that. And we want to make sure we're very precise with how we type this in, because anything that goes wrong with the order of operations here can mess this up. So what we're getting here is the test statistic, and we'll go to 2 places always on this. So 1.15, so equals 1.15. That is essentially, this is a what we called a z-score. That's what that is. Okay, a z-score. Okay, so now that we have the z-score, it's time to go to our formula sheet again. And so this is on, we have several of these tables here. This is the t-distribution table. This is our normal distribution table. So this is the start of it. But we need to find that z-score that we had over here. We want to find the 1.15. Let me go back over to this left display. And so we start on the left side here. Here's 1.1, right? And then we go over to what that 5 is, right? So right here, okay? And this percent, or this value here, is not the p-value that we're looking for, because we remember that these tables only, look at this little diagram here, these only show the areas to the left. So let me actually clip this real quick so that I can write on it just a little bit better. 1 point. Okay. Move that over to my other screen. Okay. So we are interested in the greater than. This is a right tail test. And what these tables show are the left. So this would be a left tail. Okay. What we want for the answer for this is this side, right tail. So you do need to keep track of the direction of this test, okay? And I'm going to definitely make examples with 2 tails as well, which is the not equal to. We will get to that. But you have the left and you have the right tail. We need the right tail. So when we look at this, 1.1 over to 5, we have this, right? that is not the answer that we actually need, because what we're looking for is a p-value, and that would be a very, very large p-value, and it's unlikely that we'll see many p-values that look like this. So this is a concern here. This means that the result is very likely to have happened, but we're going to basically do 1 minus this, the right tail. So I've done that already, and here we get this value here, 0.1251. So the p-value equal to 0.1251. And so that's really what we were looking for when we're running this significance test. So calculate this test statistic. We did that. Then use the normal distribution or the t-distribution tables to find the p-value. Now we've done that, okay? Now it's time to interpret these results. So we had a lesson over interpreting the results of these values, and that happened with this. We were talking about if the p-value is smaller than alpha, we say that the data are statistically significant at level alpha, okay? And we had these little general statements down here: p-value less than, p-value greater than, we reject or fail to reject. So here, especially for AP students, it's super important that you are specific in the language here, okay? So we say the p-value is less than alpha of 0.05, because it actually, every question is going to tell you the alpha level. So they tell us here, right? Okay, 0.05. So we fail to, and hold on, p-value is not less than, it's greater than, sorry. I did that last on another example. The p-value is greater than alpha of 0.05, so we fail to reject HO. I'm going to write it like that. H0. Okay. The test is not statistically significant. There is not convincing evidence that more than 8% of the potatoes have blemishes. There we go. That's how you want to interpret this, and that is how you work a full question of one of these significance tests. So all of those concepts go into place right there. Okay. Good. Next, we're going to work one more question. This time we're going to be doing doing one for mean. Okay, so I'm going to go ahead and spoil that for you. This one's going to be based on the mean, but we're going to speed things up a little bit, and I'm going to have to write on a separate page for this because I've sort of filled up the space here. So it says we've got level of dissolved oxygen in a stream or a river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So we have all these values. It says a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. First part, there's two parts to this one. A, do we have convincing evidence that at the alpha equals 0.05 level that aquatic life in this stream is at risk? So we're going to have to run a significance test. So we go for part A. Part A here. Okay, so we want to run this test. The first thing we want to decide, is it mean or is it X bar? And now I've already told you that it's mean, right? Looking at that right there, which we don't want to interpret that way. That's not necessarily going to be the case. We just want to look at the actual question itself. And when you read it, there's not really anything that stands out as far as like mean, standard deviation, percents, proportion. We don't see any of those words, but I will go ahead and say this. Anytime you see data like this, it's going to be means. Okay. The only thing to do with this is quantitative data. It makes sense to take a mean of it. So we're going to be doing means on the problem. We're going to say, okay, this is X bar. X bar. And then the next question that we have to ask is sigma known? And that's a question. That's not a, we don't know yet. So do we know what sigma is in this question with this mean? We don't see the word standard deviation. So that kind of tells us right away that no, we don't know what sigma is. So no. That means this is an indicator that it's means unknown sigma. That means we're probably going to end up doing a t-test. I'm going to put that t-test. Just be prepared for that. That means we're going to be using the t-table for this. Okay. So that's okay. So step one, let's create the hypotheses. HOHA. Okay, HOHA. What symbol are we using? Are we using P or mu for this? Well, since it's means, we got to use mu. We always start with our symbol first. It's gonna be one or the other. So the mean. This is always an equal to. All right, now we have to figure out what are they trying to show? What are we trying to seek evidence for? Do we have convincing evidence that the aquatic life in the stream is at risk? That's what we want to know. Is there evidence for that? And it says a dissolved oxygen level below 5 milligrams per liter puts the aquatic life at risk. So below 5 milligrams per liter, so less than 5 is what we want to know. There we go. That's how we set that up. Okay. If you're still confused about these hypotheses, there's plenty of practice that I can give you if you need more, just like setting those up. We can do that because that is so important for this. Okay. We got to do all the checks first off, and I'll write these out. Is it random? 10% normal, right? That's what we want to know. It's always going to be that. So is it random? We read here, researcher randomly chosen, right? 15 spots. So yes, check. 10% or 15 spots less than 10% of the entire population. Well, there's pretty much an infinite number of spots, right? So yeah, that seems pretty good. Yeah. Now normal is the tricky part, right? This is less than 30. That's 15 is the sample size. So it's not normal by the central limit theorem. We don't know anything about the population. So what we have to do, and we talked about this in chapter 7, we want to check the graph. Okay, so we want to check the graph. That's what we want to do. Go ahead and make a new document in your calculator for me. So new document, no. And let's go ahead and type all of this data in. We were going to have to do this anyway to find the mean that we needed. So let's make this, I'm just going to call this X, and we're going to go ahead and type in all of these values. So we're going to do 5.3, 5.04, 3.9, 5.23, 4.13. Order doesn't matter for this, by the way. Type them in however you want. The calculator will organize them if it needs to. Just make sure that you're putting all the decimals correctly. You also want to make sure that you have 15 values. Okay, so I've got mine. If you need to pause to catch up, then go ahead and do that now. But I'm going to go ahead and go straight into the calculation. So I go over to the blank space over here. We need to, actually, no, wait. We need to make the graph. So yeah, if you need to pause, go ahead and do that. But let's make the graph. So it's been a while since we've done this, I think. But we press Control and then Dock. It'll give us a new page, and then we see add data and statistics. So we're going to click that. And then at the bottom, use your little touchpad. Down here, we want to put an X, our name our variable. So here's our graph. And really what we're looking for with this graph, obviously there's not enough data to tell if it's normal yet. I mean, it's kind of uniform at this point, but what we're really looking for is outliers. So how do we do that? Well, we really need to look at the box and whisker plot to tell if there's any outliers. So we're going to go to our plot type and change it to a box plot. And we're going to see, are there any outliers? Since the whiskers are intact, there's no extra values like separated, there's no outliers. And overall, it looks mostly symmetric. I mean, it's kind of skewed to the left a little bit, not terribly. And this is from the book, by the way. So they are saying that this one should be okay based on this graph since there's no outliers. So we are going to give this one a check mark. And we did practice that in chapter 7 a little bit. So hopefully that's okay. Number 3, we're going to run the test. So we need our test statistic. And we know that this is going to be T, right? Because we have already found, or we know that it's not a Z. So we need X bar minus mu over, how do we get our test statistic for means? Well, let's look at that formula. So down at the bottom here, you'll see these values here. If we knew sigma, we'd be doing a z-test, of course, but since we don't, we're going to have to be using this value down here for this t statistic. So I want s sub x over square root n. Also, we are going to need to know the degrees of freedom. That's going to come up because we're going to be using that t distribution table. But let's go back to our main display here. Here's our formula. Let's go ahead and use values we have. Do we know x bar and s sub x? We don't. So we actually need to go back in our calculator. Use your touchpad back over here, and then we need to find the statistics for this. So a blank space, menu 411, right? One list, and we want that list to be x, and that's all we need to do. And we get our mean is 4.77, and s sub x is 0.9. We'll round. I guess we'll just go to 4 places. That's sure that's fine. But here we'll just do 2. So this is 477 minus 5. We're going to do our calculator. We need for our standard deviation 0.9396. 9396 be over the square root of 15 because 15 is our sample size. All right, let's go ahead and calculate this. So let's I'm going to pull up my little quick calculator on the left side here. You can just click that. And so we're going to do this, make a fraction, 7 minus 5, another fraction, 0.9396, and then we want to square root 15. We get a t of, and we're just going to go to 2 places. We'll round that up. So negative 0.95, so t negative 0.95. Okay. So that's what we needed. Let's go ahead and grab our table and use that to help us here. So we need to go down to the t distribution critical values, right? So here's the table we were on. We go down here, okay? So what we're looking for is the value that matches that t statistic that we just got, right? And you'll notice that absolutely none of these values are negative, okay? We are going to have to use the absolute value of this t distribution. By the way, this does give us the right tail on here. So right here it says, look at this. So t star, that's what we found, is probably p lying above it, and the probability c lying between negative t and positive t. Okay, but we're really just interested in one of these tails. We want the left tail, but if we can find the right tail, we automatically could find the left tail because they are in fact symmetric. Okay, if we needed a two-tail test, then we would add both tails together. We would just double the value. Okay, that's what we would do. But hopefully we'll make sense of this. First off, let me clip this because our value is 9 or 0.95. We don't have any negatives, so we're just going to go 0.95. So let's go back to the table now. And we're looking for 0.95. Oh, also, We also have the degrees of freedom. Do you need that? That's n minus 1, which is going to be 14 here. So that's got to play a part as well. So let's go over here. So that's really where we should start. Here is the 14th degree of freedom, and we're looking for 0.95. Okay, so we'll go back over there, and you'll notice that that's not on the table, right? It's not on there, but it has to be between these values, right? 0.868 and 1.76. So that means, so these values up here, it has to be between those probabilities. That's what that P is right there. It's the probability. So we know our P value has to be between 0.2 and 0.15, or we'll order them the other way around. So we're going to put this, so we're going to say P value is greater than 0.15, but less than 0.2. That actually is helpful still, even though it doesn't sound as precise, right? It is going to be helpful when we go to do our interpretation, because that means that the p-value is greater than alpha, because we know our alpha level is 0.05. Okay, so that is actually very helpful. Very, very helpful. So this is sort of a similar conclusion to what we just had. So I'm going to actually go back over here, and we're going to copy at least the first part. Actually, no, we're going to go to here. The alpha level is in fact the same. Loads, good grief. So the alpha level is in fact the same. So we're saying the p-value is greater than alpha of 0.05. So we fail to reject HO. The test is not statistically significant. There is not convincing evidence that the aquatic life of this stream is at risk. That's what we were trying to figure out. Is it at risk or not? Well, the p-value, there's not evidence to say that it is at risk. Okay. Now we have part B. It says, given your conclusion in part A, which kind of mistake, type 1 error or type 2 error, could you have made? Explain what this mistake would mean in context. So we failed to reject HO. So we go back to our table here of conclusions. Here's our conclusions. We failed to reject, right? Failed to reject. Means the only error we could have done was type 2 error, which means we failed to reject when it was false, or the alternative was true, which means what? Well, we said it wasn't at risk when it actually is at risk. That's what it means in context. So when we're reading this, explain what this mistake would mean in context. So for part B here, have it is possible type 2 means that the aquatic life is actually at risk. Find evidence to support that. Okay, that's what that means. And so that's the errors, getting those back into play here, reminding ourselves of those. But those are definitely the types of questions that you'll probably be asked on different types of tests. Those different types of errors and what they mean. All right, so I'm going to stop the video there. Questions, let me know. I'll probably put up another video working the other two questions I had. So, and then you have work on Kitim that you can do now. So, all right, I'm going to go ahead and stop.